Welcome to CS 103. This is linear algebra for machine learning. These videos are the lecture videos, and there is a corresponding textbook called Linear Algebra for Computer Science, LA for CS, and there is an associated website called laforcs.com, and each class, each session is going to correspond to one chapter in the textbook, and this is chapter 1. So today we will be talking about expressions, functions, equations, and linearity. That will be the starting point of linear algebra. Let's get started. By way of introduction, let me try to answer this question that I keep getting from some of my students. Why would I want to learn linear algebra for computer science? Why learn some heavy-duty mathematics? The thing to understand is that computer science really is applied mathematics. We might have thought of computer science before we started learning computer science, that it is something like programming, software development, etc. But at the core of it, it is actually mathematics. Linear algebra is a part of the theoretical minimum that you need to be a good computer scientist. The way I look at it is this. If you want to be a writer, you cannot get away from learning words and grammar and the basic sentence structures, etc. That is the basic minimum that you need to be a writer. Similarly, if you want to be a boxer, you have to be brawny, you have to be strong. You cannot ignore strength and then try to learn just boxing. It will not work. It is along the same lines that you need mathematics for computer science, and in particular, this specific branch of mathematics, linear algebra, happens to be the one that is most appropriate for computer science and data science. Let's see why. It's because all modern data sets are just huge tables of numbers, as you know, features along columns and observations along rows, roughly. And they are matrices. Matrices are best handled using tools appropriate and available in linear algebra. You cannot really build any kind of computational algorithm without having this background and this foundation. In machine learning and deep learning, for instance, neural nets are basically a mapping between two different vector spaces. It's a nonlinear mapping, but it's a mapping. It's expressed and developed using the syntactical edifice that is linear algebra. Linear regression, as you shall see later in this course, is actually a beautiful and elegant application of linear algebra using projection. More generally, in any kind of data science project that you get started with, you want to reduce the dimensions so that you can track the problem in a finite computer. And that is done using a technique called principal component analysis, PCA, which, at least in principle, is done using something called singular value decomposition, which is actually the last chapter in this textbook and the last class in this course. So all those things are supremely relevant to computer science and data science. In Google, the foundational algorithm that made Google stand out from the rest of the pack when it comes to web search was actually a linear algebra algorithm called eigenvalue decomposition, which is a precursor to singular value decomposition, thinking of the whole internet as a connected graph and trying to find the most important nodes in that graph. And that was Google PageRank algorithm. And as you know, that made Mr. Larry Page, the proponent of that algorithm, a billionaire many, many times over. So it is not merely an academic exercise knowing linear algebra. It can have lucrative impact in your bank balance. Concepts like covariance between different features turns out to be a matrix product after having done a bunch of basic pre-processing in the data, like zero centering of the data. So statistical quantities like covariance can come out of linear algebra also in a very computationally efficient fashion. Matrix factorization also forms the backbone of things like recommender systems. When you look at what is recommended for you in Netflix, for instance, behind it, what is running is actually a linear algebra algorithm, rather an algorithm that is based on linear algebra. In graphics, if you are into video games, you should know that the viewpoint of different players in a multiplayer game is actually implemented using linear algebra. Transformations and rotations of scenes, etc. They are all done very efficiently in linear algebra. In fact, without linear algebra, it will be impossible to do those things. In NLP, natural language processing, word embeddings, which will be a way in which you put the words in some kind of a semantic space, a space of meanings of words, that is done using linear algebra also. Even the very idea of a semantic space, a latent hidden space inside the space of the co-occurrence matrix of all the words in the language is actually something from linear algebra. The reason why students ask me these days why they have to learn linear algebra is because of large language models, which seem to know everything that I will be telling you in this course. And then you might ask yourself, why should you know this? Because all you have to do is to spend $30 a month, and things like ChatGPT and Gemini might be able to tell you all these things anytime that you need it. But that notion is actually a bit misplaced because LLMs themselves are developed using the concepts of linear algebra, like word embeddings in huge vector spaces and neural networks, etc., transformers. Those things have their own limitations, not merely in terms of what we are typically fond of saying, that the creativity aspect will be stunted if you don't learn the basics of it. That is true, that is one part of it, but they are limited, even mathematically. They cannot go beyond the building blocks that actually built it. You, computer science students such as yourself, will be the people later in life who will be actually able to improve upon it, develop new algorithms, and enhance its capability. You don't want to stop the march of human progress in terms of knowledge creation at today's level, which is what will happen if you start learning everything that LLMs know now. You have to create new knowledge, and that, I believe, can be done only by learning the basics, and there is nothing more basic than the foundational mathematics, linear algebra being one significant part of it. Now, if you step beyond computer science in the last 100 years or so, everything that happened in physical sciences also came out of linear algebra. Quantum mechanics, the language of quantum mechanics is actually pure linear algebra. If you look at a textbook in quantum mechanics after having done this course, you might find it weird because they use different notations like angle brackets for vectors and vector products, etc. But it is actually the same linear algebra that you learn here, with some extensions like vectors are actually not real vectors but complex vectors over the field of complex numbers, and the space, the dimensionality of those vectors is actually infinite because vectors are actually wave functions encoding the probabilities of different events. But with that proviso, quantum mechanics can be understood, at least mathematically, completely after this course. Special relativity also uses linear algebra. In fact, one of the basic genius aspects of Einstein was the fact that he was able to formulate the problem of relativity in terms of linear algebra. He put it down as a linear problem, and then he wrote down a matrix of transformation between two different frames of reference, and the norm of those vectors, norm being the size of the vector, will turn out to be invariant, constant, which is easy to see if you have a vector in 3 dimensions. If you just rotate the vector, you don't change the size of the vector. You cannot change the size of the vector by rotating it. Similarly, rotating a vector in 4 dimensions, which is what special relativity is talking about, will keep the speed of light constant, and that is called Lorentz invariance, and that is what special relativity is all about. Going beyond that, in other physical fields such as electrical engineering, Kirchhoff's laws can be expressed elegantly in terms of linear algebra, and actually the computational tools dealing with Kirchhoff's laws does its thing using linear algebra formulation. And there are Fourier and Laplace transforms, and associated with that, fast Fourier transforms. All those things are basically implementations of linear algebra, either theoretically, as in Fourier and Laplace transforms, or as algorithms, as in FFT. Those things all come out of linear algebra. The field of applicability of linear algebra is actually so wide that nobody will be able to tell you all those things in just a couple of slides. There is so much more to it than what I can tell you here. Even the foundational things like the golden ratio, as you will see toward the end of this course, comes out of linear algebra, and the Fibonacci series of numbers can be thought of as some kind of matrix multiplication. Again, something that you will see later in this course. Now, before we move on to the next part, I just want to tell you one more thing about the station of linear algebra in your mathematical life. This is going to be the course that will take you from mathematical infancy to mathematical maturity. What I mean by that is this. There are so many little fields of mathematics that you learn. Geometry, algebra, and then connecting those things, coordinate geometry. All those things sound like different, distinct fields disconnected from each other. And linear algebra will start telling you that these things are not different branches, really. They're all aspects of the same thing. So this gives me a chance to philosophize a little bit. What's mathematics? Mathematics really is a formalization of the patterns that you see in life, in reality. Truth is what is encoded in mathematics. And to the extent that truth is singular, mathematics has to be singular too. And that realization will start happening to you from this course. You will see that complex numbers, well, I won't explicitly tell you, but hopefully you will appreciate that complex numbers are basically linear algebra in 2 dimensions. And all those things are generalized in linear algebra. And to the extent that the mathematics of life is just one, when you realize that, that's when you start loving mathematics, so to speak, because the immense volumes of beauty that you have in this universe, they are all written in the language of mathematics. And that realization comes with mathematical maturity, which is what I would strive to convey to you. But of course, you will have to come with me. But before doing all that, we have to answer the first question, what linearity really is. Linear algebra contains the word linear in it, and then we have to kind of explore that. That will be the next video.